In this lesson, we're going to look at population growth. And particularly, we'll talk about the time it takes for a population to double. For some populations, like bacteria, the doubling time might literally just be a matter of minutes or hours. For populations of people, it might take thousands of years or maybe decades. How that doubling time gives us information about how quickly a population is growing. So the doubling time of a population is the amount of time it takes a population to double in size. Calculating doubling time helps you understand how fast a population is growing. The table on the next slide gives historical estimates of the human population. All right, so this is a table. It gives populations in terms of millions. You may not be familiar with this letter, or you may not. BCE means before, whoops. Erase that. Okay. BCE is before the Common Era. We are currently in the Common Era. CE is the Common Era. Those are fairly new terms. The older terms, the ones I'm actually more familiar and more comfortable with, were directly linked to Christianity. We had BC, which meant before Christ, and we had AD. AD comes from the Latin for Anno Domini, which translates as the year of our Lord. And it refers back to the year Christ was born. So we have a period of before Christ and a period after Christ, or beginning with Christ. That I'd say is more commonly, and I guess many textbooks now, they use our Common Era for our current counting of years, and BCE before the Common Period. If you look back 10,000 years BCE, the human population was about 1 million. Okay. 1,000 years later, it had grown to about 3 million. Okay. You can see now that it's grown all the way to 6,864 million. Now, 6,000 million is actually 6 billion. And in fact, if we look up for 2020, that's around 7, and that's not as exact, but about 7.8 billion is our current population, or 7,800 million. This table gives us a lot of information if we look at it. And we're going to come back and we're going to look at it several times. What does the entry 8,000 BCE mean? It means 8,000 years before the Common Era, or before Christ. What's the world's population? 8,000 BC. 8,000 BC, that's right here. We can see that the world population was 5 million. So what is our goal? We want to understand that growth can be measured in terms of doubling time, and that doubling times can be used to compare growth during different periods. How is the population growing now compared to how the population was growing 1,000 years ago? We want to calculate quantities in the billions, use data to estimate doubling times, and just compare and contrast growth via doubling times. How long did it take for the population to reach double that amount? Well, I think we're going back. Let's look to what they're talking about. Question 1, what was the population 8,000 BC? How long did it take to double? Well, look, it was at 5 million, and it doubled when it reached 10. So it went from 8,000 to 6,000. It took 2,000 years to double. So the answer is it took 2,000 years. How long did it take? So that was going from 5 million to 10 million. So if we want to double again, we want to go from 10 million to 20 million. Go back. So how long did it take to go from 10 million to 20 million? It took another 2,000 years. So at least in this part of the table, the doubling rate seems pretty constant. Find at least 3 other examples of doubling population in the table. It doesn't have to be exactly double. For example, Earth's population doubled between 500 BCE and 81, a period of 500 years. Record some notes that can explain your thinking. Discuss your results with your group. Was the doubling time always the same? What does this tell you about the rate of growth of the human population over time? So let's go back and look at more doubling times. Well, from here to here, the population doubled. We went from 50 million to 100 million, and that took 500 years. And let's come over here. If we look at some fairly easy numbers to work with, this is about 6 billion. Let's go here to here. 1.262. If we doubled that, we'd get a little bit over 2.5. From here to here, 1,262 million to 2,519 million, that's approximately doubled. How much time did it take? 1850 to 1950. Oh my goodness. That's only 100 years. That's from 1850 to 1950. The population went from about 1.25 billion to 2.5 billion. Okay, let's double again. 2.5, if we double it, would give us 5. We don't have to be exactly 5, but let's go. So approximately from here to here, we've doubled again. So from 1950 to 1990. That's only 40 years. Something's definitely going on. In these earlier times, it was taking about 2,000, let me get this straight, it was taking about 2,000 years to double the population. Then only 500 years, notice from here to here, also took 500 years. So they've cut the doubling time down considerably. But all of a sudden, if we jump way up to about 1850, now the doubling time's been cut to 100 years. And then from 1950 to 1990, it's cut to only 40 years. Our population is definitely growing faster and faster. Notice here, we go up a whole billion people, a billion people from 1990 to 2005. In less than 15 years, we've added a billion people. It took us 2,000 years to add 2 million people. This is incredibly faster. So, what did we learn? The doubling time wasn't always the same. In fact, the doubling time has been getting much, much shorter. And that tells us that the human population is growing much, much faster. Which of the following statements best describes the changes in doubling times before 1800 AD? Before 1800 AD, estimated population doubling decreased from 2,000 years to 1,000 years. That's not really true. They decreased even more than that. But this is true. The doubling times generally decreased. We saw it go down really to less than 500 years. But we know that doubling times definitely decreased. Write a statement that describes the change in doubling times after 1800 AD. Doubling times after 1800 AD were much shorter than before 1800 AD and are continuing to decrease. What are some factors you think may have led to this change? Why are there so many more people? Really, it's about improved health. And it's improved health at both ends of this spectrum. One is we've had a dramatic decrease in infant mortality. At one time, if we go back even just a couple hundred years, at least 1 out of 5 children died before their 5th birthday. Infant mortality was high. But you have to remember, we had no antibiotics. We had nothing to treat illness other than home remedies. We just did not understand about viruses and bacteria. So if your child had an ear infection, they either got better or they didn't. They got a strep throat. It either got better or it spread to their heart and caused all kinds of problems. The other place is because of this improved height, is an increase in life expectancy. People are living longer than they have ever lived. And both of those are also probably related to an increased food supply. There are still parts of the world that are troubled with food supplies, but compared to 500 years ago, we're much more efficient with agriculture. We can raise many more pounds of food on an acre of land. So all of those things, and you may think of other factors. This is, imagine that you're explaining the relationship of million, billion, and trillion to someone else. You may use words, symbols, and pictures. It says your response should follow the guidelines found in resource writing principles. Well, I don't currently have a copy of this, so I'm not sure exactly what this resource would tell us, but I can explain it. I know that 1 million is 1,000 times greater than 1,000. In other words, 1 million is equal to 1,000 times 1,000. I know that 1 billion is 1,000 times greater than 1 million. So 1 billion is 1,000 times 1 million, or and finally 1 trillion is 1,000 times greater than 1 billion. So we have 1,000 times 1 million, 1 billion rather, when I write this in terms of the numbers of zeros, 1,000 is 3 zeros, 1 million is 6 zeros, 1 billion is 9 zeros, and 1 trillion is 12 zeros. That's going to help us in just a minute as we move into writing things in scientific notation. All right. In the world of science, and in just in the world in general, some numbers are really huge. Here's a really huge number that we really do use in physics, and it looks like this. See if I've got this right. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 15, 18, 21, 20. That is it. I'll write that in kilograms. That's a hard number. I don't even know how to read it. It's definitely more than a trillion. And after about a trillion, numbers get really hard to read, even if you go through and you put in all your commas. But that's the mass of the Earth. If you're trying to send a rocket to the moon, you need to know the mass of the Earth. There's other numbers that are difficult because they're so small. That number's really small. It's not a millionth. There's a millionth. It's not a billionth or a trillionth of a kilogram. It's much, much smaller than a trillionth of a kilogram. This is the mass of a proton. Again, numbers that are really useful in science. So science in particular is one place, but it's not the only place. Economies, where you start talking about billions and trillions of dollars, where the numbers are so long, they're difficult to read. At the beginning of this course, you worked with your class to answer the question, how big is a billion? In reality, there are things so large or so numerous that thinking in billions is not large enough. Similarly, there can be things so small or rare that thinking of them as 1 billion is still too big. For example, have you ever thought about how many ways a deck of cards can be shuffled? I honestly haven't, but a deck of cards has 52 cards. There's a lot of different ways you can combine and put in order 52 different cards. So, we want to understand that very large and very small numbers can be represented in different ways. We want to be able to represent large and small numbers in scientific notation, and we want to be able to convert those things from scientific notation back to standard notation. Oh my goodness. So this number is the different ways to deal a 52 card deck. It's a very large number, and it's impossible to get an idea of how large it is just by looking at it. One way we express very large or very small numbers is by using scientific notation. To use scientific notation, we essentially think about the number using multiplication. If we go back to lesson 1, part A, assume that the average shoulder width of the people in the line was 1.325 feet. So one person had a shoulder width of 1.325 feet. How long would the line be if it contained 10 million people? Well, one person is 1.325 feet. So if I multiply that by 10 million, I'm going to do it a couple of ways. First, I'm just going to write 10 million. 10 times 1.325 is 13.25 million feet. So if I write it with the word, it's a little easier to write. Or I can write it out, 13,250,000 feet. Round the answer to the nearest million. Well, to the nearest million, that would be 13 million. Or if I want to write it out, that's 13. How many zeros? Well, look at it. That's 6 zeros. When we're in the millions, that's what we expect. Rewrite the answer using multiplication. Well, one of the easiest ways to do it is say, 13 million is simply 13 times 1 million. Just think of a different way to express the number and write it down. Well, one of the ways we can do it is thinking in terms of powers of 10. This is a really important idea. We know that 10 to the first power is simply 10. 10 to the second power, I don't know how many of you remember exponents, means 10 times 10, and it equals 100. 10 to the third power is 10 times 10 times 10, and it equals 1,000. Well, a million has 6 zeros. It's simply 10 to the 6. So we could write it as 13 times 10 to the 6. That would be another way to write 13 million. A number in scientific notation is written in the form A times 10 to the n. So it looks like this. But this number, it says, has to be between 1 and 10. In fact, it can equal 1, but it cannot equal 10. So this number, we wanted to write A is greater than or equal to 1. But less than 10. Let me go back and show you what I wrote. That's not scientific notation, is it? Because this number is not less than 10. How do I fix that? I need to fix it. I can change this to, think about 13. That can be 1.3. But if I make this number 10 times smaller, this would have to be times 10 to the 7th. That's going to be scientific notation. I want to show you what happens. If we think about 13 million here, in order to make this number less than 10, I have to move it so that there's only one digit in front of the decimal. So I move the decimal 1, 2, 3, 4, 5, 6, 7 places. Since I moved the decimal 7 places, to move it back, I have to multiply by 10 7 times. So in scientific notation, our answer would have been 1.3 times 10 to the 7th, or in standard notation, it looks like this. Notice that when you have large numbers, the exponent is positive. I want to make a little table of values. It's probably helpful just in case you didn't learn some of this. If we look at, let's just start with something that's not always obvious. 10 to the 0 is equal to 1. It's hard to explain why that's true, but I want you to accept that as true. 10 to the first is equal to 10. 10 to the second is equal to 100. Notice how the exponents here, when we have a positive exponent, they just tell me how many zeros. And of course, 10 to the 6th, we've already said it's a million. And 10 to the 9th is a billion. Okay. For numbers less than 1, the exponent is negative. We still have a situation where 10 to the 0 is equal to 1. 10 to the negative 1 is 1/10, or 0.1. 10 to the negative 2 is 100th, or 0.01. Notice you can make a relationship between this. 0.1, you'd have to move it one place to get it back to be an integer. 10 to the negative 2 would be 2 places. 10 to the negative 3, that is 1,000th. It's 0.001, etc. That is 1/10,000th. I want you to see, anytime the exponents are negative, you know that in standard form, the number was less than 1. Anytime the exponent is positive, in standard form, the number was greater than or equal to 1. Okay, use what you've learned to express the number of ways a 52-card deck can be shuffled in scientific notation. So let's go back and let's look at that number for that 52-card deck. There it is. We know the first part of the number has to be 8. We need a number that's less than 10. Usually we put a couple of decimals. So if we're going to keep 2 decimal places, that 5 is what we look at. That's going to round up to 7. So our number is going to start off 8.07 times 10. And now we simply see how many times we'd have to multiply by 10 to get back. So we start here. It's going to be a lot. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32, 33, 34, 35, 36, 37, 38, 39, 40, 41, 42, 43, 44, 45, 46, 47, 48, 49, 50. Oh my goodness. 51, 52, 53, 54, 55, 56, 57, 58, 59, 60, 61, 62, 63, 64, 65, 66, 67. We want to put our decimal right there after the 8. Whew. That's multiplying 8.07 by 10, 67 times. That's huge. It's still, even in scientific notation, almost mind-boggling large. That was our answer. How does expressing this number in scientific notation change the way you understand the number? Well, at least makes it easier for me to read it. I can read 8.07 times 10 to the 67th. I can even know that if I compare 8.07 times 10 to the 67th, and I want to compare it to I know this is 1,000 times bigger because it's got 3 more, right? It's got multiplied by 10 3 more times. 10 to the third is 1,000. I can at least have some idea of how it compares to other big numbers. You can see 10 to the 67 is 1,000 times bigger than 10 to the 64th. The chance of an event happening can be described using probability. For example, there is a 1 in 2 chance of having a baby girl, which is the same as a probability of 1/2, or 0.5. I want to start by saying that slide's a little misleading. There's a 1 in 2 chance of a pregnant woman having a baby girl. If you're a man, the chances are 0. So 1 out of 2, that's how we get our probability. 1 chance out of 2, that's the same as 1/2. Or we can write that as a decimal, 0.5. If I want to change a decimal to a percent, I can do that by multiplying by 100%. So another way of stating the probability is that there's a 50% probability, or a 1 out of 2 chance, or probability of 1/2. The probability of having identical twins is approximately 0.0035, or 35 10,000ths. Remember, this is the thousandths place. This is the 10,000ths. So this is 35 10,000ths. In scientific notation, what does that look like? Okay, remember, this number is smaller than 1, so I know the exponent will be negative. I move it 1, 2, 3. I always move it so there's exactly 1 digit. That's 3.5 times 10 to the negative 3. Sometimes it's useful to use standard notation instead of scientific notation. To express a number in standard notation, just write out the number. Well, let's show you how you write it. Okay, 7.56 times 10 to the 4th. That means you're going to multiply by 10 4 times. Every time you multiply by 10, the decimal place moves over. So you're going to move the decimal 1, 2, 3, 4. You're going to have to fill in those zeros. It's going to be 7, 5, 6, 0, 0, or 75,600. Or if you prefer, you can probably type this in your calculator, but you could think of it, that's times 10,000, 10 to the 4th, 4 zeros. Well, 7 times 10, that's going to be 7. You can see, we'll get the same thing. Okay, that concludes this lesson. We'll discuss some more examples when we have our meeting.